Today we are looking at the heat equation for a rod when both ends of the rod are perfectly insulated. The heat equation itself stays the same as before. It says curly du by curly dt equals alpha times curly d squared u by curly dx squared. Here, u of xt is the temperature at position x along the rod at time t, and alpha is a positive constant called the thermal diffusivity. Because the ends are perfectly insulated, no heat can flow in or out at either end. This means the boundary conditions are zero flux conditions, not zero temperature conditions. In symbols this says curly du by curly dx evaluated at x equals 0 and curly du by curly dx evaluated at x equals L equals 0. This is different from a rod with fixed end temperatures. There, separating variables gives sine eigenfunctions. Here, separating variables gives cosine eigenfunctions instead. We separate variables by writing u of xt equals x of x times t of t. Substituting into the heat equation splits it into two ordinary differential equations, one for x and one for t. Solving the equation for x together with the zero flux boundary conditions gives the eigenfunctions x sub n of x equals cosine of npix divided by L for n equals 0, 1, 2, and so on. The matching time part decays exponentially. It is t sub n of t equals e to the negative alpha times open bracket npi divided by L close bracket squared times t. Putting these together, the general solution is a sum. U of xt equals a naught divided by 2 plus sum from n equals 1 to infinity of a sub n times cosine of n pi x divided by L times e to the negative alpha times open bracket n pi divided by L close bracket squared times t. The coefficients, a naught and a sub n, are found from the initial temperature distribution by matching it to this cosine series at time t equals 0. This is called a Fourier cosine series. Now think about what happens as time goes to infinity. Every term with n greater than or equal to 1 contains a decaying exponential, so every one of those oscillating terms shrinks away to 0. This leaves only the very first term, a naught divided by 2, which does not depend on time at all. This constant equals the average value of the initial temperature taken across the whole rod. This surviving constant is called the steady state or equilibrium solution. It is the single final temperature the whole rod settles down to. To check this, think physically. A perfectly insulated rod cannot lose any heat to the outside world, so the total thermal energy inside the rod stays constant over time. That means the final constant temperature must equal the starting average temperature of the rod, which matches exactly what our formula gives.